Okay, thank you. It's a pleasure to be here in Beijing for Strings 2016, and I'd like to thank all the organizers, Professor Yao and Wei Song and the many other people who did all the hard work to bring us here. So I'm going to give part one of a talk. Malcolm will give part two after. Oh, I'm giving, does this work? Okay. I'm giving part one of the talk. Malcolm will give part, no? Hard to stay still. Okay. I'm giving part one of the talk. Malcolm is giving part two. And parts 3, 4, and 5 will be at Strings 2017, we hope. So I'm going to talk about some recent developments that's led to, it's to here. That's led to some new insights into black holes. And the starting of this story, one has to start at the beginning. And the starting of this story is an exact mathematical equivalence between three different phenomena, each of which has been studied for around half a century. So the three corners of this triangle are, first of all, the soft theorems in quantum field theory. So the soft theorems in quantum field theory have the structure that you take any scattering amplitude and you add a particle, typically a graviton or a gauge boson, but it can also be a scalar or a massless fermion, and you let its momentum go to zero, and you find that the resulting amplitude takes the form. It's proportional to the soft factor, which I've denoted by A there, and times the same amplitude without the soft particle at all. And soft theorems are ubiquitous in quantum field theory. Quantum field theory wouldn't make sense if we didn't have these soft relations. And these soft theorems come in many different shapes, sizes, and forms. There's a lot of them across many different kinds of physical systems. The second corner is the so-called asymptotic symmetries. And the word asymptotic is a little bit unfortunate because it kind of suggests that they're not exact symmetries, that they're only symmetries in some limit. In fact, they are exact symmetries. It's just that they are most easily understood in terms of the data at the asymptotic boundaries of a space-time. And the most famous, or one of the most famous examples of this is Bondi, Metzner, and Sachs, when they discovered that the asymptotic symmetry of gravity in four-dimensional Minkowski space was not the expected Poincare group, but in fact an infinite dimensional group known as the BMS group. But this phenomena has precise analogs in quantum electrodynamics and in non-abelian gauge theories. And the third corner of this triangle is the so-called memory effect, which has been largely developed as an experimental subject. It's a long-distance effect of gravity, distinct from what's measured at LIGO. At LIGO, they looked at the oscillating pendulums, but if you analyze it very carefully according to general relativity, there's a DC effect where at the end of the day, if they are inertial detectors, there will be a finite shift, a memory of what went past. This is called the gravitational memory effect, and it's associated with the deep infrared. And there are lots of formulas in all these subjects, and what the starting point of this enterprise was discovering that all of these formulas could be transformed into each other in a relatively simple way. So let me give an outline now of the 25-minute talk. I'm going to describe the most basic and simplest example of this triangle. And there are many implications of it across different problems in physics, including amplitudes, flat space holography, jet physics, and so on. But I am going to focus, and Malcolm will continue, on what the implications of this structure is for the black hole information paradox, and then I will conclude. Okay, so I want to start at a very simple point, and that is the radial electric field from a point charge in Minkowski space. For a static point charge, it goes like 1 over r squared, and it's given by this very simple formula here. Now let's boost the charge. So you can look up in Jackson, and this is the so-called Lienard-Wiechert field, much more complicated formula that describes what a boosted charge, the electric field from a boosted charge. Now, I'm sure that Maxwell and Lienard and Wiechert knew this, but I only became fully aware of it myself a year or two ago. This formula has the bizarre property that it is not single-valued as you go to spatial infinity. And in everything that I'm going to say, this is going to play a central role, so let me carefully explain this. So here's the Penrose diagram, and a boosted charge starts at past time like infinity and goes to future time like infinity, and follows a trajectory like this. And if we take this exact formula for the electric field for just a single boosted charge, and we keep the retarded time fixed and go up to future null infinity, we find that everywhere on future null infinity, it looks like this with a minus sign. On the other hand, if we go to past null infinity first, keeping the advanced time fixed, and then up to this point, which is spatial infinity, we get a different answer. They differ by a sign. And instead of these two things being equal, they're antipodally equated. That is, if we take x to minus x, these formulas transform into one another. And the statement here is that if we take the leading part of the electric field at infinity from a single point charge, it's antipodally equal to, it equals the field at the past of the future is antipodically identified with the field at the future of the past. And this, of course, is true. It's a linear theory. If we take any number of boosted charges, it's still true. What's less obvious, but follows from formula in Jackson, is that if you let them scatter in any way and solve it using the normal Green's functions, whether it's advanced, retarded, or the Feynman-Green function, you will always find that the field is antipodally identified. Now, this antipodal identification immediately implies, with no further discussion, that all electromagnetic theories have not just one that we're used to, total charge conservation, but an infinite number of conserved charges. Because these two things are antipodally identified, I can integrate over the past of the future the electric field weighted by any component, by any function on the sphere. And taking care of the antipodal matching in this way, I can take the antipodal function and integrate it over the future of the past. And those two things are equal because these are equal. It's completely trivial. Now, for the special case that I choose this function to be a constant, I get a conservation law that the sum of all the incoming charges is equal to the sum of all the outgoing charges. And in order to understand it that way, I have to take this surface integral at spatial infinity and integrate by parts, use Gauss's law, use the constraint equations, and that enables me to write the integral of the electric field in two different ways, one over future null infinity and one over past null infinity. And I learned that incoming charge, the sum of the incoming charges is equal to the sum of the outgoing charges. Now, but I didn't need epsilon to be a constant in order for this to work. Epsilon could be anything. And what happens if I integrate by parts now? Well, now I still get a term from Gauss's law proportional to the incoming charges, but it's multiplied. Each term has an arbitrary coefficient. So the incoming charges multiplied by arbitrary coefficients summed up cannot possibly equal the outgoing charges, so we need a correction term. And you can derive that correction term by just integrating by parts. And here it is. It's a weird looking object. It's an integral. It's a zero mode, a certain zero mode of the electromagnetic field. And I'm going to call it a soft photon because it's a zero mode. It's an integral over all time. Right now I'm just discussing classical physics, but I'm going to use that terminology as soft photon. And it looks like it's contracted with the derivative in the angular directions of this arbitrary function epsilon. So it looks like a soft photon whose polarization is the derivative of this function epsilon. So at the classical level in electromagnetic theories, we have an infinite number of conservation laws which relate incoming data from past null infinity to outgoing data at future null infinity and involve all the incoming charges and electromagnetic fields and all the outgoing charges and electromagnetic fields. Now let's go to the quantum theory. So in the quantum theory, we talk about an S matrix. We have out states which are obtained by acting with S on the in states. And the conservation law becomes a statement that this charge commutes with the S matrix. Now this charge contained a term which in the quantum theory becomes an operator. It's an operator which creates and annihilates soft photons. And so we have a bizarre conservation law, in fact an infinite number, one for every function epsilon. And it relates amplitudes with a soft photon to amplitudes without a soft photon to a number, times a number, without the same soft photon times a number. So it would seem incredible that all scattering amplitudes would obey such a bizarre relationship. But in fact, it's well known. We haven't discovered anything new here. We've just said something that's been known for 50 or maybe even 100 years, the soft photon theorem. We've just derived it in a different way from starting from a conservation law. And that conservation law, its essence was just the boundary condition on the fields at spatial infinity. Now, whenever you have conservation law, you have symmetries. So we can go to a canonical formulation of the theory, and then the symmetry should be generated by this charge. And when you do that, what you find is that after you construct the Dirac bracket, make it a quantum commutator, you find that this corresponding symmetry are large gauge transformations. They are transformations of the electric field which do not go to zero at infinity. They go to a constant, but it depends on, the constant depends on the angle, not independent of angle, it's not going to infinity or zero at null infinity. And this gauge transformation is antipodally identified. So it's the opposite in the past, it's the parity transform in the past of what it is in the future. So these gauge symmetries are what we call asymptotic symmetries. They act non-trivially on physical states. We can see what the charge creates very explicitly, and there's an associated Ward identity, which is the soft photon theorem. And these symmetries are the QED analog of the BMS symmetries. And there's also an analog of the memory effect, which is described in these papers, that is the analog of the gravitational memory effect in QED. And there's also, of course, there's also a similar asymptotic symmetry in non-abelian gauge theories like n equals 4 Yang-Mills that have massless fields that go to infinity. And there's also a color memory effect. Now, this tells us something interesting about the vacuum in quantum electrodynamics, and that is, it is infinitely degenerate. So this operator Q that generates these large gauge transformations commutes with the Hamiltonian. That's obvious from the fact that it can be written as a surface integral near spatial infinity. And so if we have any state that's annihilated by the Hamiltonian, namely a vacuum state, and we act on it with Q, we get a new state which is also annihilated by the Hamiltonian, but it's not the same state. In fact, it has different angular momentum. We've added a photon, and it's orthogonal to the original vacuum state. So there is an infinite vacuum degeneracy in quantum electrodynamics, in non-abelian gauge theories, and also in gravity. And this symmetry that's generated by Q takes us from one vacuum to another. So we can describe this by saying that the vacuum in gauge and gravitational theories has soft hair. That is, it has distinguishing features associated with soft particles, zero energy particles. You can add a zero energy particle to the vacuum and you get a new physically inequivalent state. Is that the gravitational field is very weak out there, so you can quantize the theory exactly. It's a free theory. And you can compute the brackets, and you can show that these charges generate my students and I did it in this paper, that these charges generate the BMS symmetry, the asymptotic symmetry discovered in 1962. And similarly, there's an infinite vacuum degeneracy in general relativity, and the various proposed gravitational memory experiments can be viewed as experiments to actually view transitions from one vacuum to another BMS in equivalent vacuum. That's one way of describing the gravitational memory effect. Now, what does this have to do with the black hole information paradox? Well, I don't need to really review that paradox for this room, but just some of the ingredients are you throw stuff into a black hole containing a lot of information. In some short time of order the Schwarzschild radius, it settles down into a featureless hairless object that doesn't carry any quantum numbers, and it doesn't carry any conserved charges except for the mass, charge, and angular momentum. And then it evaporates, and after a long time, the system reverts to a unique vacuum state. Well, there's a flaw in this argument, and the flaw in this argument is that we can, just from these conservation laws, presuming that the conservation laws remain valid in the presence of black holes, and that would seem very plausible because, after all, they have to do with properties of near spatial infinity. And so there's several flaws in this argument. And what are they? Well, first of all, it can't be true that the fact that there are conserved quantities means that the charges must be carried by the black hole. So let's talk, for example, about angular momentum. It is always assumed that angular momentum in the process of Hawking radiation is exactly conserved, not just on the average, but exactly conserved. And that means that whenever a Hawking quantum is evaporated, is sent out, which typically will carry some angular momentum, the black hole must, its angular momentum must change by exactly the negative of the angular momentum carried away by the emitted Hawking quantum, so that angular momentum is exactly conserved. And to make this describe in a little more detail, we could imagine writing angular momentum as a surface integral over spatial infinity in some kind of weakly coupled semi-classical approximation. We could write down this surface integral, and we could explicitly see from the Einstein equation that the angular momentum, the flux of angular momentum in perturbation theory, that the flux of angular momentum going out of the black hole is equal to the change in the angular momentum of the black hole itself. The same applies, of course, to energy. The energy of the outgoing Hawking radiation must exactly equal, not just on the average, the energy lost by the black hole. Now, so this process introduces some correlations between the outgoing Hawking radiation and the quantum state of the black hole, in order that energy be exactly, and angular momentum be exactly conserved. However, energy and angular momentum are just a few of the infinitely many conserved charges that I've described. So therefore, in order for all of these charges to be conserved, there must be a mechanism for the black hole to keep track of how much of the charge it's radiated. In other words, black holes must have hair associated with these charges, which we've called soft hair. Moreover, at the end of the day, it's not true that the system settles down to a unique ground state. There are infinitely many possible ground states that it will settle down to, and it's easy to see that the conservation laws implies that there will be correlations between the final state way up here of the vacuum and the supertranslation charges carried out by the Hawking quanta. So there are many more correlations going on in this process than we had previously understood in any concrete way. And so the next step, which Malcolm will tell you about, is how we So now we are trying to understand these. Malcolm and Stephen Hawking and I are trying to understand this in a systematic way. And so just to conclude, recent developments trying to understand the infrared structure of gravity have revealed a flaw underlying the argument that information is lost. We have not, I can't say this often enough, we have not solved the information paradox, but the nature of the flaw suggests that there have been a number of things that we have been missing in our analysis of the process of black hole formation and evaporation, and there are concrete steps that can be taken to try to understand this better. So I will end there.
Any questions? One.
Now, if we have an amplitude in the LHC, these soft theorems presumably don't constrain it, right? An amplitude. If we make a measurement in the LHC, something we actually measure, the soft theorems do not constrain it, right?
Of course the soft theorems constrain the LHC amplitudes. They are the bedrocks of the calculation for, I mean, you can't do an LHC calculation without using the soft theorem. Now, I think what you're getting at is that any actual measurement involves an infrared cutoff. And so some of the deep infrared physics will be very hard to see in an actual LHC process. So I think that is part of the reason why this deep infrared structure has, a lot of it has been missed or not studied, or people talk about inclusive amplitudes. But if we're talking about quantum information in a black hole process, and we want to see that all of it is preserved, we have to understand how much, we want exact preservation of information, and it's possible in an LHC calculation process that information could go below the infrared cutoff.
Well, I guess I was going to comment that if we made a small black hole in the LHC and we measured some properties, are you predicting we are not going to be able to test information paradox because we have a cutoff in an LHC experiment?
Depending on how much information goes into the infrared, I think I don't know the answer to your question, but it's a logical possibility that information can flow into the deep infrared, and we need to quantify how much that happens. We would need to, I think it would be a very interesting question, if we want to see that information is preserved in a black hole evaporation process, how small do we need to make our infrared cutoff? And it might be that we need to make it smaller than the longest time scale in the problem in order to be sure that we hadn't lost any information.
Okay, there was one more question.
I have remembered in a paper you have chosen a spacetime without singularity, and you choose Cauchy surface to apply the conservation laws of the soft scale, and you get the conclusion that you can use the softer photons or the soft scale to distinguish the state of the black hole. And then, what if you have a singularity in the spacetime?
Well, I think in general relativity textbooks, when you see a singularity, you just draw the singularity line where the Einstein equation breaks down. And I think if unitarity is preserved, which I think most people are assuming now, if unitary is preserved, it is tantamount to saying that there isn't a singularity, that higher derivatives, stringy effects, or quantum effects somehow eliminate the singularity and allow information to go in there and come back out.